this video, we're diving into a compelling problem efficiently finding the median from a data stream. It's a challenge that tests our understanding of data structures and algorithms. We got a smart solution lined up with using heaps. So let's get started. So it's a question, find median from data stream. So the median is the middle value in an ordered integer list. If the size of the list is even, there is no middle value, and the median is the mean of the two middle values. For example, in a given array 2, 3, 4, the median is 3, and for array 2, 3, the median is average of 2 and 3, that is 2.5. So they have given a question, and with these methods where this initializes the median finder object and then void add num in, it adds the integer nums from the data stream to the data structure, and this find median is returns the median of all the elements so far. So answer within 10 power minus 5 of the actual answer will be accepted. This is the precision value they are giving. So here's the example. So the first is like median finder, add num, and this is a series of operation which they are doing. So the expected output is like this. They're just initializing the median finder, and then they're adding the number. Basically this series of operation, right? So there's adding number and then adding number and then finding the median and then adding the number like this and then finding the median. So it returns 2.0. So that's the basically a series of operation. So these are constraints where num lies between the 10 to the power of minus 5 and 10 to the power of 5. So there will be at least one element in a data structure before calling the find median. At most 5 to 10 power 4 calls will be made to the add num and find median. So this is the question. So let's dive in. So let's understand why we use heaps. So heaps are a special kind of binary tree where each parent node is ordered in respect to its children. This property makes heaps incredibly useful for quickly accessing the minimum or maximum elements. In Python, we have a min heap by default where the smallest element is always the root. For max heap, we insert the negative values instead of positive values, so the largest number will always become the smallest value in our heap context. So here let's dive in what's min heap and max heap. Right, we got two heaps here. Min heap. So min heap is a complete binary tree where we have the value of each parent node is less than or equal to the values of the child. The structure ensures that the root node always contains the minimum element in the heap. So the properties is the root node is the minimum element and the insertion and removal operations maintain the heap property. So as we see here, the root node is always less than all its children. It can be equal to also. Even if the 10 gets removed in this, it always maintain a heap min heap structure. So that's what we meant. So max heap. The max heap is a complete binary tree where the value of each parent node is greater than or equal to the value of its children. So this ensures that the root node always contains the maximum element in the heap. The properties are basically the root node is the maximum element and insertion and removal operation maintain the maximum property. So going on, we have a heap push. Heap push is a function provided with Python heap queue module, which is used to insert elements into the heap data structure, specifically in a min heap. In Python, a min heap is a binary tree based data structure where the parent node value is always less than or equal to the value of its children. So the root of a heap contains the smallest element. So when you push, when you use heap push, you provide the heap list. That is, we provide a list as an input and add the value we want to insert into the heap. This function then inserts the element into the appropriate position in the heap, so maintaining the heap property. This is how we use this function. So here heap would be generally a list and item is what the number we want to push. Here, as we discuss, the approach is using two heaps. So the strategy is we maintain two heaps, max heap and the min heap. So max heap is like it's for maintaining the lower half of the numbers and min heap is for maintaining the upper half of the numbers. So by balancing these two heaps, we ensure that they either have the same number of elements or the max heap has one element more than the min heap. So we can find the median efficiently. First thing is we had to add the number. So first we insert into the max heap and then we since we have min heap by default, we negate the number to adopt the Python's min heap implementation. So and then next step is to balance these heaps by moving the largest element of the max heap to the min heap. And then if min heap has more elements, then we move the smallest element of the min heap back to the max heap. So next step is finding the median. So if max heap has more element, then the top element is the median. So that is this is a case where odd total number of elements are there. And otherwise we have to calculate the average of top of max heap and min heap. This is for the even number of elements. So here using two heaps is just like having a two buckets to sort our numbers into two equally sized pots. With one bucket max heap always keeping the smaller half and other min heap always keeping the larger half. So this way the median is always largest number of the smaller half or the average of the two middle numbers depending on the total count of elements. So let's go to the code. So as we discussed till now, we have used the two heaps here, max heap and min heap. So self low is the max heap and self high is the min heap. This we initialize here. And then we have the second thing is to add number. So here first we add the number into the max heap by using the negation. Since we have a min heap representation in Python by default, to mimic the max heap we just make the negation of the number so that it will always be the smallest number would be at the top. So this always represent that since the maximum negative number would be the smallest number, right? So this would always be at the top. So next thing is to push from the max heap to the min heap. So here we pushing into the high self that is min heap from max heap. By using we are doing the negation again here so that it would maintain it would insert a positive element into the min heap. So next step is balancing these heaps. Balancing in the sense like if max heap has a lesser number of elements than the min heap, we balance it by pushing the one of the element from the min heap to the max heap. So and to find the median, when the max heap has more elements than the min heap, median is just the above just the top element. So we just return this one, that is have median is the 0th element here. So other case is like when this is the basically case where when there are odd number of elements. So for the case having even number of elements, the median is the average of these two things. Here max heap, min heap minus of max heap, because max heap we store the negative element, right? So that's why we do balance for the negation, we keep the minus. So minus into minus it would be plus. So it is definitely doing the average here. Don't get just confused since because we have negative sign here. So let's discuss about the time complex and space complexity. So here the rnum operation, right? So we are inserting into the heap. The insertion operation into the heap, either min or max, has a time of complexity of 4 log n. So where n is the number of elements in a heap. This is because the worst case newly added element might shifted to the up from up to the bottom of the heap to its correct position, which takes the proportional to the height of the heap. So the height of the complete binary tree's heap is log n. Hence it's a log n complexity. So and then next step is we have the balancing heaps, right? So after each insertion we may need to transfer one element between the heaps to maintain the size property, that is the difference in size between the two heaps is no more than one element. So each of this operation also has a time complexity of 4 log n for same reason as an insertion. So therefore the time complexity for this each add num operation is 4 log n. And the next operation is we have the find median. So the operation consists of returning the root of one heap or calculating the average of roots of both heaps depending on the size of the heaps. So assessing the root of a heap is O of 1, since we have directly look up, right, 0, yes, so that's why. And thus the time complexity for this is O of 1. So adding on O of 1 plus O of log n plus O of log n, the time complexity is the whichever is the maximum, that is O of log n. So space complexity. So the heap storage, basically the primary storage used in this algorithm consists of two heaps. The max heap for the lower half of the numbers and the min heap for the upper half. In the worst case, the space complexity is O of n, where n is the total number of elements inserted into the median finder, because all elements are stored within the two heaps. So other variables, the algorithm uses the constant amount of additional space for variables to track the current elements, just like the current max of and min of the heaps, which does not depend on the number of elements, thus O of 1. So in summary, the time complexity is O of log n and the space complexity is O of n. So demo and conclusion. I have got the code ready here. Let's try running this. So the solution is accepted. Let's try submitting this. Yeah, the solution is accepted here as well for all the inputs. So conclusion, by leveraging the properties of heaps, we have developed an efficient algorithm to find the median from a data string. So the elegant solution not only showcases the power of heaps but also demonstrates how combining simple data structures can solve the complex problems. So dive into the code, experiment with it, and modify your understanding of heaps and dynamic data handling. Thanks for tuning into this episode of Hack Code. If you found this video helpful, be sure to give it a thumbs up and subscribe to the channel for more coding tutorials and problem solving tips. So if you have any questions or suggestions for future topics, feel free to leave them in the comments below. Until next time, happy coding.